stiffness methods for the beams. I think we finished the topic on the truss, stiffness method for truss. Now students are in positions to complete the question 1 on assignment 1. You can complete the question 1 on assignment 1. Should be finished now. If you have not started the assignment or you have not done it, please, I encourage you to finish this question 1 assignment 1 as early as possible, because now today, after finishing these lectures, you can start taking the question number 2. You remember last week, right? If I take some revision for the last week, if you remember that last week we will take this truss or the bar element, and this bar element has 2 degrees of freedoms, can have a x and y displacement at one node, and there is another degree of freedoms x and y. So this point can go like this. It was a linear line that you can just move that line up here. We developed the stiffness matrix for these ones. I think there is a story behind it, but you don't need to worry how we get this done. So you can you calculate these ones. The main part, you remember that, right? This is symmetric matrix. Whatever the 3 numbers that you're gonna get here within plus and minus will get here. Whatever the numbers you're gonna get here, you will get the same number here. And similarly, these numbers are same. All the diagonal members would be positives. You can see all these values are on the positive. That's the one way to check whether you get a calculation right or wrong. You can also think that these boxes are same. You can think that these boxes are same. This box here and this box are same. So there is a multiple ways that you can make a check whether you done it correctly or not. And then what we done, we identify the nodes, we identify element, degree of freedoms. You don't need to worry about this one in your exams or assignment. We generally give you these assignments. We generally give you this modeling part of this one. And then we calculate the stiffness matrix for the each elements. You can calculate K1, K2, K3, number of elements that you have or number of members you have, that many K1, K2 and K3 you have. Let's say you have 5, then you need to calculate small K1, small K2, small K3, K4, or K5. This is the repeating process, so therefore we use Excel. You remember that we also use Excel. So Excels help you sometimes. Right, but you also need to do the manual hand calculations to show that once in your assignment, you can't just put the Excel file to show your details. Then we assemble the stiffness matrix for the whole capital K. So if you have a total degree of freedom, let's say 8 total degree of freedoms, you will get the K 8 by 8 matrix. If you have 12 total degree of freedoms, you will get 12 by 12 matrix. It's a big matrix that you will get. And then we get the load vectors, force vectors, and you will get the displacement vectors. And we use this Q equal to KD relationship. And from that Q equal to KD relationship, we solve du, and then we solve the reaction force and internal member forces. And we also take an benefit of representing whether it's in axial internal force or is a tensile internal force or the compression internal force. So far, that's what we cover, right? So you are in the positions, if someone give you the truss, you are in the positions to calculate the stiffness matrix for each members. Then you will able to calculate the whole global stiffness matrix, the whole big matrix, capital K. You are in the positions to develop the force matrix Q. You are in the positions to develop the displacement vector D, and then Q equal to KD. You can calculate the unknown displacement, unknown reaction force, and the member internal forces. These are the details that you have calculated. Unmute yourself or put it in the chats if you think that this story that we covered last 2 weeks for the truss, it does not make sense. I highly encourage you, if you have not attended the lectures, I highly encourage you to watch the video, the recordings. You unmute yourself if you don't know how to find the recordings for those lectures before moving on to the topic here. Any overall comment or any overall questions that's puzzling you or that does not cover that in the lectures, in the last 2 weeks lectures, or that will not cover for the assignments. So let me the stiffness method of the beam part 1. After completing these weeks, you are in the positions to do the part A of question 2 in your assignment 1. Based on this one, you should be able to complete question 1 in your assignment 1. If you have not started, please do as early as possible, because you might come up with saying that, okay, I need extensions. Because there is a special considerations. If you are planning to take the extensions from now, plan ahead, okay? I'm not going to be approval for the special and take a charge before it get out of control. If you come back, it is not something that you need to do it yourself and read many books. No, just very simple. Just do it after watching these ones. Okay. All right. So this week's last week we will done the stiffness method for the truss. This week we're going to do it the beam. Now modelings are same. So we need to identify. So you remember, I always going to refer it back to the last 2 weeks. So it will give you the revision as well. So last week you remember that truss members that we have. Now that truss members has only displacement. You have X displacement and Y displacements. X displacement and Y displacement. So this guy can go like this. It can move. This guy can move from here to here. This guy can also go up and can go up as well. So there are 2 ways only possible that you can have these points. I'm talking about points, okay, not the whole things. The points that can move in the X direction. There is a point, the Y, that can move in the Y direction. That is a truss, and that is the last way. Now the beam, it is little bit slightly different. Same element. Let's say in the beam you will get vertical displacement, but there is a rotations that you get instead of X, because the beam, they don't have axial forces. They don't have anything going axially. It will have a moment. That is the moment. And it has this shear force that is going up. So that is the moment in the beam, and that is your shear force. Again, there are 2 degrees of freedoms for each node. This is, let's say, node, and this is another node. Each node has a 2 degrees of freedom. What is 2 degrees of freedom? One is going vertically up and another one is rotating. How does I physically explain you these ones? Physically explain you these ones, meaning this point can go up or down. This is a possibility that this point can go up and down. This point can rotate. That can rotate like rotations. If you understand the rotations like spinning, so that point can spin. That are 2 possibilities. Someone said, what happened to this guy? Why not axial forces? If you take a beam meaning if you have a structures, I think the telecommunication electronic students would be a bit challenging, but then for you as well, it is not so difficult. Your analytical skills would be this. Beam is something that is the horizontal members. If you have your circuit or circuit board, just the horizontal part of that one, circuit board. So you can't load the circuit board like this. It can be done bending, like it can bend or it can rotate. Okay, so the bending related to rotations, vertical displacements rotate, vertical displacements related with the shear force. So the same things here. Again, it has a 2 degrees of freedoms. Again, I will repeat it. In here again, there are 2 degrees of freedom, but there are only displacement, X displacement, Y displacement for each node. In here, you have Y displacements and you have rotations. The displacement relate with the shear force. What is shear force? That someone might ask. Shear force meaning that if you have something and you are trying to do shear meaning if you are pushing one end and pulling going up another end, then you will creating the shear. I hope you understand the shear thing. So for example, this is the pen. This is the pen. If left side I will do it, right side I do it, that is shear. So in this cross sections it is shear. Like if I tear the paper, if I want to tear out the paper, I can show it to you. I can't tear these papers if I do it both this way. One I need to hold, another I need to do it this way, right? So you can see both two ends. If I do it both same hand, I can't tear the paper out. So you need to have, this is a shear force that you are pulling this end from left to right. Hello. Parsons? Oh, thank you. Thank you for that. Yeah, sorry about that. So we have this shear force, that is the displacement that will create, and we have a moment that will just the rotation. So again, if I put it into the format that you have these displacements, that green black arrow, and that is represented by D and Y dash. I can explain you all these notations. D stand for displacement, N stand for near node. Now there is a location vectors. You remember in the truss as well, so we will have location vectors. The tail of the location vector recognize the near node. Head of the location vector recognize the far node. Okay, so that's how you do it. So this D stand for displacement, N stand for near node, Y stand for the vertical displacement in the Y direction, dash stand for the local axis, X dash Y dash, local coordinate system. So I hope you understand the meaning of D and Y dash. That is how we going to represent them. Then you will have this force which is related to this the so you need to read it this one separately. Like this one is separate, and this is the force to create these displacements. Displacement will not create by itself. You need to push this n to make it d and y dash. How much force you require to create d and y dash? That is q represented by force, n is near node, y direction, and s dash. So I hope you understand that. So d and y dash. So you can read it two separately. D and y dash, amount of force required to create d and y dash displacement is a q. Then you have this point I'm talking about, it can rotate. Now, this rotation is about z axis. If I have this x axis going this way, y axis this way, z axis is coming out of my screen. That is a z axis, and that's the rotations that is created. So this that is again, the rotation is one kind of a d displacement, one kind of a degree of freedom. At near node, about the z axis in the local coordinate system. So I hope you understand that is a rotation, d and z axis represent the rotations, and d is a displacement, is a rotations, and n is a near node, z and dash. Now to create these rotations, we need some kind of a moment or force, moment force. So that is represented by q at the near node about z axis and dash. Right. So I hope you understand those terminology for here. Similarly, we have same thing. This point can go up. So for that case, we have a vertical displacement at the far node going in the y direction in the local coordinate system. To create these ones, we need the force to create this displacement at the far node in the y-axis and dash. Similarly, you have this displacement far node about the z-axis, which is a rotations. Locals, to create this one, we need this qfz dash. Okay, so I hope you understand the notations here. Unmute yourself that if you does not make sense, where any of these numbers and f, location vector, x dash, y dash, all these numbers that I putting it here, that if you don't understand, unmute yourself that this particular name intention that I don't understand before moving on to the next one. Everything is looks okay to me. Now sign conventions, we need to make some assumptions. This is based on assumptions. There is no hard and strong rules. Probably this one is the book and all, probably this is the term rules and all, so we can follow. It is better we can follow it, but this is just an initial assumptions. Do not change your assumptions, like whatever I'm putting it in the lecture note, do it exactly the same thing. Otherwise you end up with some positive negative, and you end up with some errors. Make your life easy. Make your life easy means which what I'm telling you, that you need to take the force and displacement are positive when they follow the coordinate system. Moment and rotation are positive when they act in the anti-clockwise. So When you have anti-clockwise, then that moment is positive. So when you have anti-clockwise like this, then you will take the positive moment. So always make an assumptions at the start saying anti-clockwise is positive. That is your assumption, and you don't change this assumption throughout your examples. It is just there and staying there. OK, it's just assumption that we make it at the start and we don't change it. So everything will have the same sign conventions throughout your examples. There is no any engineering logic here. You just these right hand thumbs rules and all this physics that they want to follow for these rotations. OK. Now modelings. We done it in the trust as well, and I'm going to explain you this one here as well. When you get the figures, you will get the figures like this. This is your questions. They will not give you the modeling, right? They will not. Let's say someone putting the load P here. That's load P. And this one is fixed and this one roller and some dimensions. Now, first thing first, when you see the number in the square is the element number. When you see the number close in the in the square brackets, you will see that one is a element number. When you see this arrow, it is your location vector. Arrow is a location vectors. It's representing your near node and far node for this element number 1. For this element number 2, near node is here and far node is here. So it is just arrow is going to help us to identify the near node and identify the far nodes for that particular elements. That is the location vector. You will see the number with the circles 1, 2, and 3. Let's say 3 and 4. The number with the circles is going to give you the node number. Node number 1, node number 2, node number 3, node number 4. And someone say, what is node? If you take an element and if you just take a two end of the elements, it is their nodes. It's just the end point of the each element. So that is the node. So I explain you these square brackets, circle. I explain you this one. Now, when you do the modeling, what you do, you put the degree of freedoms. Let me clean up this all things so you will understand. And there is no logic so far to see which one is 1 or which one is 2. You can make it 1, 2, or 3. There is no logic. 1, 2, 3, 4. Someone might put 1 here. Someone might put 2 here. Someone might put 3 here. Your answer will not change. There is no logic for you to say this is 1, 2, 3, and 4. You can put 1, 2, 3, 4 arbitrarily. Is a user defined. There is no rules that you need to follow to make it 1, 2, 3, 4 or 1, 2, 3, 4. Just need to identify those numbers and they will stay as it is throughout the example. So there is no rules to identify the element 1. There is no rules to identify the circle ones. There is again no rules to have a location vectors. To be pointing in this direction, you can put the location vector in this direction. There is nothing wrong in that one. OK, so there is no rules. But once you make the decision of those 3 things like a square numbers, number within the circle, these location vectors in the examples, you don't change it. Now, once you've done this, then the next step would be to let's say you have this, and here this ones. Next step would be to make a degree of freedom. So here you have degree of freedom, vertical degree of freedoms, you have rotation degree of freedom. You have vertical degree of freedoms, you have rotation degree. Every node where you put those degree of freedoms. You have every node, then you put the location degree of freedoms. OK, that is the degree of freedoms that we going to put it. Now, there is a rules for this one now. There is a rules for the numbering. When you have free degree of freedoms, free meaning, because you can see there are 2 kind of degree of freedom, free degree of freedoms, and there are fixed degree of freedoms. Okay, again, you remember that free and fixed degree of freedoms. Let me write it here. Free degree of freedoms and fixed degree of freedoms. How many total degree of freedoms here? You can see total because each point has a 2, 1, 2, 3, 4, 5, 6, total 8 degree of freedoms we have. Now out of 8, we need to identify which one is the free degree of freedom and which ones are the fixed degree of freedoms. How do we recognize that? When you look at the support, when you look at these supports here, these supports, there are fixed degree of freedom. So in here, this one is fixed because this point which I'm fixed, it cannot rotate, it cannot go up. So this one fixed, this one fixed. You with me, right? So at node number 1, you have 2 fixed degree of freedoms, which is let me put X here so you can represent a fix. So there are 2 fixed degree of freedom. Unmute yourself that you don't understand that because the point is fixed, meaning that that point cannot rotate, but this point is not fixed. OK, I'm just talking about the point where is supported. That is the point. Don't be confused that OK, all these points are fixed. No, in between this point, they are not fixed, or they are free to rotate and free to displace. In here, this point, which is the roller can make it this one fix because roller don't allow to go up and down that point. I'm talking about again point. I'm not talking about the whole this next point next to it, very small point. It can go up and down, but this point which is particularly sitting on the rollers, it cannot go up and down. So that is fixed, but it can rotate, right? Because this point is rotate because they're not fixed. So it's not like a fixed support. So this one is free degree of freedom. This point here, there is no any support here. It can be freely rotate and freely displayed. So this is free and this one is free. So they have 2 free degree of freedom. Similarly here, this point cannot go up and down and it would be free. Sorry, this one would be fixed, but this one would be free. Do you understand these ones, right? If you just take a point, think about it, that if it is fixed support, meaning that displacement and rotation are fixed. If it is a roller, meaning that it can rotate, freely rotate, but it cannot vertically go up and down. If it is spin, still you cannot go up and down, but it can rotate. So I hope you understand that. So when you have free degree of freedoms, that is your starting point. 1. There is another free degree of freedoms. Let's say 2. Let's say 3. Let's say 4. So there are 4 free degree of freedoms. So let's say 1, 2, 3, 4, and these are your unknown as well, unknown degree of freedoms, right? So 4, so 1, 2, 3, 4. Yep, there are 4 free degree of freedom, and remaining are fixed. 5, 6, 7, and 8. 8 are no one displacements. Right? I hope you understand that. So there is a rules that free degree of freedoms, you need to start with 1, 2, 3, 4. Now you may ask me the question that looks complicated. Do you gonna give us in the exam or in the assignment? Yes. In the assignment and exams, all these details will be given to you. All these details given to you, meaning that this one with the round is given to you. One with the square bracket given to you. Location vector given to you. This numbering is given to you. This axis given to you, X and Y. Everything is given to you as a modeling. You don't need to do it the modeling because there is no any logic that we wants to test your engineering knowledge. There is no any, it's just the art that you can develop by doing practicing. OK, so we're not going to check your knowledge or your understanding on this modeling, but you need to understand, you need to know why this numbering here, what is this number, why they are in the number 1 in the square bracket, in the circle 1 in the circles and location vectors and so on. So that's the understanding I put it for you. Unmute yourself that if you think that you don't understand anything so far in the beam, or any questions before moving on to the next one. What I said, that degree of freedoms, let's say you have this beam. This is the beam given to you. Now this beam has a node. That is node number 1, node number 2, node number 3. Circle with this one is node number 4. Circle number is your node number. Now, each node has a degree of freedoms. How many degree of freedom? 2. One is a displacement and another one is a rotations. And I put positive degree of freedoms because positive here, positive here. I don't know whether it is correct or not, but then we can change it. Each point has a 2 degree of freedom because this point can have a possibility of going up and down, and it can have a rotations. This point has a degree of freedom going up and rotates. This point has a degree of freedom going up and rotate. Right? So that is the each node has a degree of freedom, and those degree of freedoms are this vertical displacement and rotations. Okay, does it answer your questions? Let's move on. Now we want to create the displacements. Sorry, we want to create the stiffness matrix. We want to create the 4x4. There are how many degree of freedom for each element? There are 4 degree of freedom for each element. It can go up and it can rotate. It can go up and it can rotate. So there are total 4 degree of freedoms for each element. Right? Let's make it. Let's release. So this is the beam element, and it can, this point can go up and down, and it can rotate. This point can go up and down, and this point can rotate. So there are 4 possibilities that I'm talking about for the beam. Now what happens if I fix these ones, and I can also make a slider. Slider meaning like this, sliders. Slide like sliding doors. If you go to if you have a house and all, you have a glass sliding door. So it is a sliders. So what these sliders will do, that these sliders can allow freely to go this point up and down. Do you with me? All other degree are fixed. This one fixed because this point cannot rotate. These guys fix here because these guys cannot go up and down, cannot rotate. So at the moment, I have only this point can go up and down in this one. You with me? So I fix this one. This is a slider. So this point can only go up and down. Right? This is the first thing I done. I arrest. I arrest meaning I put the clamp at that point. I make it all 0. I make this one 0. That is no rotation allowed. You can't rotate. This ones you can't go up and down. I make it 0. This one, this point cannot rotate. I make it 0. Only possibility I left is to go up and down for this particular point. You with me story in this so far in this story? What I have done, because you understand that this beam element has a 4 possibility. It can go up and down at the left side. It can go up and down from the right side. That is 1, 2. It can rotate number 3. It can rotate number 4. So there are total 4 different degree of freedoms. Out of 4, I remove 3. I fix them. I make it them 0. Only I leave 1 possibility. Yes, so far so good. In that story, you with me. Now, to create that displacements, you need the force to create the amount of, because I have this one fixed and there is a slider here, right? Now I say that I'm just allowing this displacement, and let's say this is location vector, so that's become near node. So that is D and near node Y dash. This is the only displacement I allowed. So let's say I don't know this displacement, so let's make it this one 1. Let's make it this one 1. Now, based on, because this material has a Young modulus and it has a moment of inertia. Now you may ask, what is Young modulus? What is Young modulus? Every material has a stiffness. Every material has a stiffness means when you apply the force, it will have a resistance to deform. Some materials can be easily be able to deform. You can just like a rubber. elastic rubbers, you can just stretch it. That is the Young modulus, very small. Some, when you pull it, still it's very difficult. That is a Young modulus. You put it in a machine and you can just draw the stress strain curves, and that slope that you're gonna get it is a Young modulus. It's just the measurement of how stiff the material is. How stiff meaning how stretchable the material is. So that is a Young modulus, right? Because the beam should be made of steel or concrete, or if you have electronics peoples or electronics people, they may be made of some kind of a polymers or something. So they have a Young modulus. Okay, yeah, it can be any value. And who gonna give you? Your manufacturer. The suppliers may know this Young modulus value. If you have materials which you don't know, you can go in the lab, do the tensile testings, and you can calculate the Young modulus. Now, what is I? What is I? I is a moment of inertia. Moment of inertia meaning that how difficult to something to bend. That is the I. If the I value is small, which is the moment of inertia, inertia meaning resistance, resistance against the moment. If I have this bar and if I want to rotate it, how strong it is required to rotate it, how strong it is. So that is the measurement of, that is a geometric property. You can make it in a shape that will have a very high I value. I meaning you can't bend it. If it is small I value, you can easily bend it. Okay, that's how it is measuring the I value, moment of inertia. This is a geometric property and E is the material property. So I hope you understand the story. So based on E and I value, the amount of force that required to deform that one would be 12 EI on L cubed. Let's say this is the length of the bar. So amount of force that required to create the unit displacement one vertical is 12 EI on L cubed. That is a whole story behind this theory, how I get it, but that is the what can I say? That is a theory that based on Young modulus and I and length, I would have this displacement. You can look at this one. If I have more E and more I need more force to create this ones. If your length is increasing, that is inversely proportional. If your length increase, it is very easy for me to do this one. So if I have very small value, it is very difficult. If I have long length, I can easily do it. So that is 12 EI on L cube. So I hope you understand that amount of force required to create the unit displacement 1 centimeter, 1 millimeter, 1 meters unit displacement. There is no unit. There is no unit for one. Let's say that's 1. We just say 1. So if you use an elastic range, and if we say that this one become D and Y dash, then these guys also become D and Y dash, because if you multiply 1 by D and Y dash to make it displacement D and Y dash, you multiply by the force by D and Y dash. That is here written. That amount of force required to create the displacement D and Y is this one. Right, you hope you understand that. Now, if you is fixed on the other side, you will have reaction force. So on the other side, you will get reaction force far end in the verticals, negative because it's going down. You can look at that. I repeat the story again. First, I said that I apply the unit force. Amount of force required to create the unit force is 12 EI on L cubed. I explain you E, I, and L. But I don't want 1. I want displacement to be D and Y dash, would be any value. So I change it that 1 to the displacement near node in the Y directions. So I multiply the whole things by D and Y, right? And once you have this force here, it will be fixed here. So there is a opposite and equal reaction force. So that is 12 EI on L cube. Now, for how much, because this will, once you have this force here, it will also create a moment, because this is a fixed support, right? This is a fix on the other end. So it will create the reaction moment as well. That reaction moment would be 6 EI L square D and Y dash. And similarly for equilibriums, you have on the other side as well 6 EI L square on D and Y dash. So this is the displacement required to cause this, to create all these reaction forces and shear forces and so on. And if I put it in these notations like Qn force, and Z. This is near node force. In the Y direction Z, this is far node force. And if I put it here, 12 EI cube 6 EI L square minus 12 6, and I put this one D and Y dash, you will get all these stiffness metrics. I hope you understand. Don't worry if you don't understand all these behind story. I will give you one magical equations that we're going to use it. But I just want to have a feeling of where it's coming from. OK, in the exams or anywhere, you don't need to draw all these diagrams or you need to remember anything. All this notation, all the equations will be given to you. You just need to use your understanding and concept. As you can see in the assignments, you can open all lecture notes, everything that can help you. Now, what about next one? That I can fix this one and I will make the opposite. I will fix this one and I will make the slider here. I will make so in that case, your far node is going up. So amount of force required, let's say amount of force required, let's say there is only one. Let's say I want to apply the 1 unit force. Amount of force required to create this one is minus 12 EI on L cubed. That is the force that you require to create this 1 unit load. So if I have to have a reaction force going in the opposite directions, which is your 12 EI on L cubed. Similarly, you get the reaction moment here as well because it's a fix. So when you have fix, there is a rotations that you are restricting. So that's 6 EI on L square, and you put it in this format, you will get this one. So what I done, I try to go up and down on the left side, fix everything. Then I fix everything, go right side up and down, and I create these force patterns. Similarly, someone wants to rotate this point, right? Like you remember, we have 4 possibility. We have one going here, another one here, one going here, another one here. First, we done this. Case number 1. Second, we done this ones. Now we are making free this one and all others are fixed. So if I want to rotate, this end by 1, let's say I want to rotate this end by 1 radians. So amount of moment required to rotate this end is 4 EI on L. And if you just multiply this one by theta, then you multiply by theta. And then the reaction moments that you're going to create is the half. And from there, you can just you can think of the notations here. Theta A is your D and Z test, and that's become your 4 EI on L, and that's become your 2 EI on L, and that's the force, that reaction force that is created. OK, so that's again I put it in the matrix format, and that is the stiffness matrix that we get. Now next, case number 4. That last coordinate that I applied the unit rotation here. I want to create the unit rotation. Amount of moment required to create the unit rotation would be 4 EI on L. That is 4 EI on L, and this rotation is represented by D, F, Z dash. And the reaction moment would be 2 EI half, that goes on the other side. All these reaction force that's also created because of these fixed supports. And that's, you put it in the equations and put it in the matrix forms, you will get all these 4 different cases. You remember this first case? The first case was this one slider. Second case that we done is this one fix and this one slider. Third case, we make it this one rotate and this make it fix. And the fourth case, we make this one fix, we make this one rotate. Right? So there are all 4. Case 1, case 2, case 3, case 4. If I combine them all, this is force, come here, and I have these columns here, this third one here, second one here, third one here. I will get this stiffness matrix. Bang, this stiffness matrix that we're going to use it this week. So that is the stiffness matrix for the beam. Again, same story meaning that you will have these guys same as these guys. These are same as these ones. this one same as this one. All these along the diagonals, you always get the positive value. You always have a possibility to check this one. These guys would be same as these ones. These guys would be same as these ones, right? So this is the one that we're going to use it to find the stiffness matrix of the elements. Okay, we almost talk about 40 minutes, and we will not ask you to remember this. You don't need to remember these equations. I will repeat again. Please do not waste your time to remember all these equations. It is just for you to understand. I show you how they come out, how we derive that equations. If you don't understand, still you don't need to know, but you just need to have a feeling of how you derive that equations and where those numbers are coming from. So we can start working on the examples that will be more useful to do the your what can I say your assignment questions. But let me know if you have any questions there before moving on to these next values. Any questions there? All right. If there is no any questions, no one is talking. If there is no any questions, we need to determine the stiffness matrix K of the beam so on. In the figures, you can take Young modulus. Both Young modulus are same. If it is different, then we need to use the different strategy. So both has the same EI value. All right. Now this is the one stiffness matrix. Now for this one, what we need, we can just get the equations that will be useful. Where is my magical equations? Here you go. We can take these matrix equations, copy and paste. So that magical equations would be useful. Probably the modeling is given to us. Yep, here the modeling is given. So let's get the modeling done. There you go. The modeling is also given to you. All right, so we need to calculate. Let's say we will get the element 1. And let's draw the element number 1. So here you go. Element number 1. Location vectors given here. Oh, let me draw at the same spot. So it will not be element number 1. Length of the element is 2 meters. Length L equal to 2 meters. And if I want to draw the degree of freedoms here and here, degree of freedoms here and here, it is given 6 and 4. So 6 and 4, it is given 5 and 3. Right? Let me know, and let's say node numbering 1 and 2, that is given. So I'll stop here. Let me know the writing which I done element number 1. And when I draw these figures, you don't understand some of these details. You let me know. So far, so good. I draw the element number 1. And I draw degree of freedoms. I draw 1 square bracket to show the element number 1. I put degree of freedoms 4635. All right, all good so far. Now, if you understand these ones, then if I just use these equations, bring it down here, then it would be more useful to keep it in front of us. Just keep it in front of us. Now in here, I can see this EI is, I can see this EI is everywhere the same. So I can take the common out EI. So I can write 12L cubed. I can write 6L square. I can write minus 12L cubed. I can write 6L square, 6L square, 4 on L, minus 6 on L square, 2 on L, minus 12 on L cubed, minus 6 on L square, 12 on L cubed, minus 6 on L square, 6 on L square, 2 on L, minus 6 on L square, 4 on L. Can you see it? That what I done? I just took the EI out because EI looks everywhere the same. Because it will be more, we can do it those step by step, because we don't want to do it all this one in one go. Okay, otherwise it will become too bulky. So I took the EI out. Unmute yourself that you don't understand what I done, or any of this row or any columns that you don't understand. I put the EI out because the EI looks common all throughout the matrix. So if you with me, then there are some common things. 12 on L cubed. So 12 on 2 cube is 12 on 8. Where is 2 coming from? This is length of element 2. Length of element 1 is 2 meters. So I substitute that. 12 on 8 would give me, let me use my calculators here. 12 divided by 8, it give me 1.5. You with me? 6 on L square, which is here. So 6 divided by 2 square, 6 on 4, 3 on 2, 1.5. 4 on L, 4 divided by 2.5. Anything else? That's 2 on L. 2 divided by 2 equal to 1. I hope you understand. I just done it very quickly, all these elements. So now let's substitute the value. K equal to EI. And 12 on L cubed. 12 on L cubed is 1.5. 12 on L cubed is 1.5. 6 on L square. 6 on L square is 1.5. 1.5. This minus sign, we put minus. 12 on L cubed. 12 on L cubed is 1.5. 6 on L square, that is positive. So 6 on L square. Thank you for pointing it out. So we so far so good. 6 on L square, 1.5. 4 on L, 2. Minus 6 on L square, minus 1.5. 2 on L, 1. Let me fix up this guy here. Okay, now minus 12L cube, which is minus 1.5. Minus 6 on L square, minus 1.5. 12 on L cubed, 1.5. And minus 6 on L square, minus 1.5. 6L square, 1.5. 2 on L, 1. Minus 6L square, minus 1.5. And 4 on L is 2. Right? Check, check, check. Diagonal positive. One check done. This line, row 1.5 minus 1.5, same. Second check done. Minus 1.51, minus 1.51. Third check done. Fourth check done. This guy here. think somewhere something wrong. -12 outlet. And there would be the minus sign in here. Let me check my book. Now there's another one that does not work, so that's okay. We don't need to check these guys. So only those checks would be enough. So I don't want you to just blindly follow it. You can make these 4 checks like diagonals and all these rows and columns. If you make any mistakes, you can catch it by yourself and make it corrections. Go back and check and make sure that they are on the spot. Okay. Now few things I like to highlight with you that you can make it this one. This one is your near node. The first 2 columns are near node. So the near node is 4 and 6. Oh, sorry, the 6 and 4. The rotation, the vertical displacement first. So 6 and 4. You understand that? Vertical displacement first, rotation that one. And this one far node, vertical displacement and rotation 5 and 3. 5 and 3. So 6, 4, 5 and 3. Unmute yourself if you don't understand that. First 2 columns are for near node, and the first columns are the vertical displacement of the near node and then rotations. Vertical displacement and rotation do not require to do any remembering. Just all right. If you have no questions, we can further move on to the element number 2. What is the element number 2 look like? Exactly the same. Element number 2. Here you go. Element number 2. Oh, sorry, that is not our things. This one here, rotation. This one here, rotation. The numbers that we can put in is 3, 5, 1, 2. 3, 5, 1, 2. And the length is 2 meters. Location vectors going here, number 2. And length is equal to 2 meters. So I think it's exactly the same. K2 because length is same. So we can put same thing. EI 1.5, 1.5. If the length is same, you can make it exactly the same. 1.5, 1.5, 1.5, 2, minus 1.5, 1, minus 1.5, minus 1.5, 1.5, minus 1.5, 1.5, 1, minus 1.5, 2. Right, and in here, our matrix would be vertical first, near node, because this is your near node based on this tail and head. So vertical is 5, rotation is 3. Vertical is 5, 2, rotation is 1. So 5, 3, 2, 1. Okay, that is your element number 2. Unmute your capital K is equal to K1 plus K2, which is your stiffness matrix. Now, what is the total degree of freedom here? You can see we have total degree of freedom 6 because you have 3 nodes. Node number 1, node number 2, node number 3. Maximum number is 3. 3 times 2 is 6. So we need 6 by 6 matrix. Capital K, EI is constant. And from there, you can make 1, 2, 3, 4, 5, and 6. And you can make 1, 2, 3, 4, 5, and 6. There are 6 by 6 matrix that you can put it there. Now 1 1, these numbers here that we're gonna make it is 1 1. So 1 1 is 2 here. Is there a 1 1 here? There is no 1 1, so just 2. Column 2, row 1. Column 2, row 1, minus 1.5. You with me? And there is no any column 2, row 1, otherwise we need to add them. Again, column 1, row 1, column 3 is 1. Column 1, there is no 4. Is there a 4 columns here? There is no 1, so that is 0. Column 5, row 1, column 5, row 1, 1.5. So I hope you understand this game. It's just like putting those numbers where it's supposed to be in terms of 1 and 2 and 3, 4. And column 6, row 1. Column 6, row 1, there is nothing, so that puts 0. Now row 2, column 1. Row 2, column 1, minus 1.5. Minus 1.5. Row 2, column 2. Row 2, column 2, 1.5. Column 3, row 2. Column 3, row 2, minus 1.5. Column 4, row 2. Column 4, row 2, there is nothing. Column 5, row 2. Column 5, row 2, minus 1.5. And column 6, row 2 is 0. Now row 3, column 1 is 1. Row 3, column 2, minus 1.5. Now column 3, row 3 is 2 here. And column 3, row 3, 2 here. There are 2 plus 2 is 4. Column 4, row 3. Column 4, row 3, 1. 1. Column 5, row 3. Column 5, row 3, 1.5. Column 5, row 3, minus 1.5. So that is becomes 0. I hope you get the story. So I can just write it down for you. Column 4, 0, 0, 1, 2, minus 1.5, 1.5. 1.5 minus 1.5, 0, minus 1.5, 3, minus 1.5, 0, 0, 1.5, 1.5, minus 1.5, and 1.5. I hope you understand that. Let me know if you have any questions. So this is the one. Now in here, we can get the modeling. The modeling would be, there you go. That would be our modeling. Where did it go? There you go in our modeling. And we need the equations. Copy, and we need these equations here. Okay, we can put these equations there. All right, so let's do this here now. All right, in here, we can have a element number 1, same story. We can draw up the elements. Don't worry about the forces when you calculate the stiffness matrix. The forces will not come into the pictures for the stiffness matrix. It will come later. It's just E, I, and L. So this is element number 1. Location vector is here, and near node and far node 1 and 2. Location vector, near node, far node, 1, 2. You have 4 and 3. So you have 4 and 3. And you have here 2 and 5. Here you have 5 and 2, right? And the length of this one would be 6 meters. Length would be 6 meters, right? So I hope you understand that. So no any issue. We just get these informations for you, and we can get these matrix here closer to us, so we can work it out. So again, K equal to EI. Let me put the EI outside. 12 L cubed, 6 on L square, minus 12 on L cubed, 6 on L square, 6 on L square, 4 on L, minus 6 on L square, 2 on L, minus 12 L cubed, minus 6 on L square, 12 on L cubed, minus 6 on L square, 6 on L square, 2 on L, minus 6 on L square, 4 on L. So now let's crack this. 12 on L cubed, 12 on 6 cubed. Let me calculate that. 12 divided by 6 cubed, you get 0.056. 6 on L square, 12 on 6 square. So 12 divided by 6 square, you get 0.333. Let's get 3 decimal places. 4 on L, 4 on 6, you get 0.667. And then you will get 2 on L, which is 2 on 6. So 2 on 6, you get 0.333. So let's plug the value K1 EI. You get 12 on L cubed, 0.056. 6 on L square, 0.333. Six on L square. Oh, here you go. Some mistakes here. 6 on L square. So 6 divided by 6 square, you get 0. Just correct this one, 0.167. So you put here 0.167. And then you have minus 12 on L cubed, minus 0.056. 6 on L squared, 0.167. 6 on L squared, 0.167. 4 on L, 0.667. Minus 6 on L squared, minus 0.167. Minus 0.167, 2 on L, 0.333. Then minus 12 on L cubed, minus 0.056. Minus 6 on L squared, minus 0.167. 12 on L cubed, 0.056 and minus 0.167 or 6L square. 6L square, 0.167, 0.333, or 2 on L minus 6 on L square, minus 0.167 and 0.667. Near node, far node business, 4 up, round 3. So 4, 3, 5, 2. 5, 2. 4, 3, 5, 2. Check, check, check. All positive diagonals. Good. This line same. These guys same. These guys same. 1, 2, 3, and 4 check done. K2. Element number 2. Element number 2. Here you go. We draw 2, 5, 1, 6. One here, one there, one here, one there, and we calculate get 2 and 5. So here you got 2, here you got 5. Here you got 1, and here you got 6. So here got 1, 6. Length equal to 2 meters. I think 2 meters. Yep, 2 meters. 1 plus 1 is 2 meters. And the location vectors going here. So this is near node, this is far node, and this is element number 2. You remember this element K2 equal to 1.5. I think if you go back here, you know length equal to 2 meters, then we can use this exactly the same 1.5. If you calculate that one again, because it's just dependent on the length. AI, let's keep it out. So if you want, you can put 1.5. Like last time we done it, right? You done it 2 times. 1.5, 1.5, 1.5, 2, minus 1.5, 1, minus 1.5, 1.5, minus 1.5, minus 1.5, 1.5, 1, minus 1.52. Near node, far node business, 5, 2. 5, 2, near node, 6, 1. 6, 1. 5, 2, 6, 1. Diagonal all positive, check number 1. This line same, check number 2. This line and this check number 3. And these are same, check number 4. All done. So now K equal to K1 plus K2, 6 by 6 matrix. Total degree of freedom is 6. You can see there. Total big number is 6. 3 nodes times by 2. So if I want to have capital K, EI is out. You get 1, 2, 3, 4, 5, and 6. And then you will get 1, 2, 3, 4, 5, and 6. In here, column 1, row 1. Let's go and get it. Column 1, row 1 is 2. Do we get here? No. So there is a 2 here. Column 2, row 1. Column 2, row 1 is a 1. And similarly, you can just copy that. Numbers, if you have 2 numbers, you can add them. I'm just copying it from my solution, but you can unmute yourself and say that particularly these numbers, I don't get it. I'm happy to elaborate more. Minus 1.5, 1.5, 0, 0, minus 1.5, 1.5. Again, all the diagonals are positive. Or is it too fast? Or is just completely unknown territory? Something come up? It is okay. Thank you. One student said okay, so I take all okay from other students as well. So what we done so far, that we develop, I can show it to you. We develop this, you remember the stiffness matrix that we develop. I don't want you to blindly follow these ones, but I want you to take these ones, let's say, and put it in the Excel in here. Okay, let's put it one somewhere here for the reference. Let's get another one. We need the modeling one as well. Let's get this modeling one. So let's get this copy and let's put this modeling one here as well. That's what we needed. What else we needed? We also need that magical equations. That will be useful, right? Okay, where is the equations that we use? Here you go. And that equations that we can put it right there. Copy. Okay, right there. Okay, let's reduce the size here. We don't need that big and put it here. Right, you with me? And what about one not? Does it load it here? Sometimes it loaded, sometimes it does not. EMS5CAE. Yep, it is loaded. So you remember that we done this. These guys here. Let's see if we can get these guys done it. Okay, so what we done? Stop me if it does not make sense. Okay. Let me get that. Let's say we want to have a. Let's put this one a little bit up so we can see. Let's say we want to have a element. Right. So let's say we have element number 1, and if you have element number 2, right? You have element number 1, element number 2. If you have 5 elements, you can put 1, 2, 3, 4, 5. Let me put underline this ones. Let me put that one bold. So we know that is element number 1. Now for element number 1, the important quantity is the length. We need length in the meter. So if I have a length in the meter, what would be the element number 1 length? It is given here 2 meters. So let's put 2 meters. I put these meters here and let's make it in the middle. And element number 2, 2 meters. So element number 2, 2 meters. Now, we also have a Young modulus. Probably we have a load in kilonewtons. So just put it in kilonewtons and we have a length in meters. So that's fine. We can go back to our lecture notes and show that we have a Young modulus 200 gigapascals. Now, what is the meaning of 200 gigapascals? 200 gigapascals, let me open that here. Now, what is 200 gigapascals meaning? Let me draw it up. So Young modulus equal to 200 gigapascals. What is gigapascals meaning? Giga meaning 10⁹. You with me? That if I want to have it giga, I can remove that giga and I can put 10⁹ pascals, right? I hope you understand that. Now pascals I can write into the 200 times 10⁹ pascals. I can write Newton per meter square. 1 pascal is equal to 1 Newton per meter square. But I want this one in kilonewtons. You can see that. I can see it. I need in kilonewtons because my load is in kilonewtons. So I can just divide it by this whole thing by thousands to make it in kilonewtons. So I can say that 200 times 10 to the power 9 become 10 to the power 6 because 10876 kilonewtons I can write now, and kilonewton per meter square. So I can write 200 times 10 to the power 6. So I can write 200 equal to sign times by 10 to the power 6. I hope you know how to do it. Just put the equal to sign, type 200 times 10 to the power 6 using your keyboard, press enter. Does any students following with me? Does any students doing Excels with me? Or just only me? Otherwise I can slow down.
Yes, sir, we are doing with you.
We are doing with me. So this speed is fine.
Okay, sir.
Yep. Just stop me if it is goes too fast. OK. All right. So just type these ones. E and both. Similarly, we have same Young modulus for second one. So just you can just click on that one, copy, click on these ones and just Control V. Just put it in the middle. I will just give us some time to catch up. That Young modulus is done. Another one that you have moment of inertia I, and we also need in meter to the power 4. I, which is moment of inertia, let's say underline, and we can just make it I, meter to the power 4. If we go in our lecture note, I is given 120 to the power of 10 to the power 6 millimeter to the power 4. So I can show it to you that I equal to 120 times by 10 to the power 6 millimeter power 4. 10 to the power 6 millimeter power 4. So 1000 millimeter equal to 1 meter. So I need to divide this whole thing by 4 times. 1000 to get rid of 1 millimeter to the meter. Another thousands to rid of second millimeter to meters. Another thousands to rid of third millimeters to the meter. And this one another thousands. I will get this this meter to the power 4. So 120 times 10 to the power 6 divided by 4 times this one. So we can do that. So equal to 120 times 10 to the power 6, I believe, divided by, let's put brackets, thousands to the power 4. Right? That's what we wanted, right? We just make it, maybe we don't need brackets, just thousands to the power 4. And that's your meter square. So here you can put this one meter square. So that is your I. Now we have few things, 12 EI on L cubed, or we can do it 12 on L cubed first, like we done it in the 12 divided by L cubed. So you can have, let's say this one's underline and bold and in the middles. So 12 just equal to sign 12 divided by length cubed. And you can just drag it down for the second element, 1.5. So that's what we got it, right? Remember that. Keep an eye on that number because it's not moving. Yep, here you go. What about here? Yep, 12 on L cubed, 1.5. Can you see that, right? 1.5. So that's good. Let's put it in the middle. 6 on L square. 6 divided by L squared. 6 on L square. So equal to 6 divided by this L square. When you drag it down, this will automatically do it for you. Like this one's, look at that. 6L squared, that is automatically done it for you. 6L squared done, this one 12L cube done, 6L squared done, this one 4 on L. 4 divided by L. So then you will have 4 divided by L. You get 2. And you can just scroll it down. 4 on L. And then you will need to do it 2 on L, last one. Control C, Control V. 2 on L. You will get 2 divided by length. You get this one. I hope you understand that. Now we can make it this element number 1. Let's say element 1. Just write it. So far, so good. You still holding there? Let me know if you fall behind. I can stop and wait for you to catch up, or anything that does not make sense. So far, so good. No response. So element number 1, let's put the detail. Let's give them name K1, like we done it in here. And let's give them some dark color here, and then 1 2 3 4 1 2 3 4 by 4 matrix, and let's give them some color here, and let's put it all borders. Okay, so first thing first, 12 on L cube. I just put EI outside, equal to 12 on L cube, this one. There you go, right? Let's put everything in the middle. Equal to 6 on L square, 6 on, and this is element number 1. So I'm picking all this element number 1, 1.5 minus, equal to minus 12 on L cubed, which is this one, 12 on L cubed, equal to 6 on L square, 6 on L square. That's done. 6 on L square equal to 6 on L square positive. So good. Equal to 4 on L. 4 on L. Minus 6 on L square equal to minus 6 on L square. 2 on L. Positive. 2 on L. Minus 12 on L cubed. Minus 12 on L cubed. Minus 1.5. Minus 6 on L square. Minus 6 on L square. Minus 1.5. 12 on L cube positive. Equal to 12 on L cube positive. Minus 6 on L square. Minus 6 on L square. Equal to positive 6 on L square. 6 on L square. 2 on L equal to 2 on L. And equal to minus 6 on L square, minus 6 on L square. And 4 on L equal to 4 on L. This one's okay. So you can compare this value with our calculations that we done. Remember 1.5 or 1.5 minus 1.5, 1.5. They are all sitting down here. And we can put those numbers there. You remember these numbers? 6, 4, 5, 3. Yep, we can put that. 6, 4, 5, 3. And let's put this one in the middle and red. Middle and red. And 6, 4, 5, 3. And that is on this side. Okay. We can make this K1 here. Again, let's put it in the different different key ones, let's say. And we need 6 by 6 matrix, right? Because you remember that 6 by 6 matrix 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. So let's put this one into just lighter colors and put these details there. So here we need 1, we need 2, and by the way, you can just drag it like this. 3, 4, 5, 6, and 1, 2. You can put it like this, right? And we just drag it 4, 5, 6. Okay. Now 6, 6, 1.5. So let's equal to this number 6, 6. Let's make it everything center. 6, 4. 6, 4. There you go. 6, 4. 6, 5 minus 1.5. 6, 5. There you go. 6, 3. 6, 3. Here you go. There you go. Then 4, 6. 4, 6 here. 4, 6. 4, 4. 4, 4. 4, 5. 4, 5. 4, 1. Oh, sorry. 4, 3. 4, 3. There you go. 5, 6. 5, 6. Here you go. 5, 6. 5, 4. 5, 4. 5, 5. 5, 5. 5, 3. 5, 3. Then 3, 6. 3, 6. 3, 4. Sorry, this one. 3, 4. 3, 5. 3, 5. 3, 3. 3, 3. All done, right? Just leave all these ones 0 or just leave it empty. That should not be any issue. Now for element number 2, you can just select all these and we can make it here. Element number 2. I think it will just going to do disturb everything. And K2. If you just, we need to use this down here, but I think it will be exactly the same. So when you click on these ones, you can just drag it out. Enter. Just drag it up and make sure it's element number 2. Drag it up, or you can just do all these things again that we done it for that element number 1. So we just drag it numbers that we wanted, because when you copy it, it will just automatically move all these cells numbers as well. So that's here. It will be quicker here by just drag and drop and press the enter button. There you go. 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 So this is all good. I think we can just change the color here. Probably some different colors. These ones to just highlight different stuff. There you go. And if you remember what numbers we are using for the next one, K2, 5, 3, 2, 1. So that would be 5, 3, 2, 1. And here 5, 3, 2, 1. We can copy all these ones. Control C. We can make it here. Maybe this one would be K2. And let's make it different colors. Let's make it this kind of a yellowish. We just separate it out. Okay, very good. Now we can just delete all this because this is different. 5, 5. So we will have 5, 5 here. 5, 3. 5, 3 here. 5, 2. Sorry, it's kind of a little bit boring for you, but this is how it is to get the full pictures. 5, 2. And once you've done these ones, I will show you the magic. This is the one first time is painful. That's all putting all these details there. But after once you've done this exercise, you can use it this one multiple times to just change the variables. Column 3, 5. Column 3, 5. Just adding it up all these one first time, so it will be a little bit challenging, but as after that would be okay. 3, 5. Where are we? Yep, 3, 5, 3, 3, 3, 2. Oh, sorry, 3, 3. So 3, 3 would be these ones. 3, 2. 3, 2 would be these ones. 3, 1. 3, 1 would be these ones. 2, 5. 2, 5. So that would be 2, 5. 2, 3. So that would be 2, 3. 2, 2. 2, 2. And 2, 1. That would be 2, 1. All right. One last one, please. 1, 5. Here you go. 1, 5. 1, 3. 1, 3. Nope, sorry. 1, 3. 1, 2. 1, 1. 1, 1. So this is all good. Now the magic is if you just want to calculate this K, which let's copy this guys here. And let's put this capital K here. Let's use different colors. This times. Let's use these colors and a little bit lighter for this. Now here we can just do one cell. This plus these cells. And that's look at the magic. You can just scroll it down like this and bang. So that will be easy for you to just when you click on here and just drag these ones across. And you can check it. Look at that cells are plussing. Look at that respective cells. And once you select all these, you can drag it down to show these all. You can check your numbers there. These are minus 1.5, these ones, and check with our hand calculations as well. Let me know if you have any questions there. The magic which I want to show you that you can use these your details versions. Like let's say make a new copy. Create a copy. Let's say this is example 1. Let's say this is example 1. And let's say I want to do this example number 2. Example number 2. Let's move these ones. Can I move it? Okay, that's example number 2. Now you remember this example number 2. Let's remove this. We have another 10 minutes. So you remember this example number 2? Oh, here you go. Let me code these ones for you. Copy. Now this part, modeling part here, we are recording. So if you fall behind, you will do it. So element number 1, you have element number 1, length is 6 meters. Look at the magic. 6 bang. Look at that. How good it is, right? You can just change these numbers. This one same, I believe. What was that numbers there? Yeah, young modulus and I you can take same, but it says constant, but you can take same. EI, let's say length changing. Look at that numbers changing. 2 is 2, the no changing because 2. So look at this. Now the numbers here we wanted is 4, 3. That's okay. 4, 3. 2, 5. 2, 5. So that is good. Okay. 4, 3, 2, 5. So we can change it here. This one we can't use it because 4, 4, we can have it 4, 4. We can have 4, 3. We can have 4, 3. 4, 2. We can have 4, 2. 4, 2. We can have 4, 5. We can have 4, 5. Now 3, 4, column 3, 4, column 3, 4, 3, 3, 3, 3, 3, 2, 3, 2, and 3, 5, and 3, oh sorry, 3, 5. And then you will get 2, 4, 2, 4, 2, 4, 2, 3, 2, 3, 2, 2, 2, 2. Okay, those numbers are keep changing. Okay, 2, 2, 2, 5, 2, 5, and then 5, 4, 5, 4, 5, 3, 5, 2, 5, 5. That's all good, right? So this is done. You can keep it all this one 0. Next one here 5, 2, 5, 2, 6, 1, 6, 1. So 5, 2, 6, 1. You can cancel all this and those numbers will automatically come here. 5, 5. So let's go back here. 5, 5. 5, 2. 5, 2. 5, 6. 5, 6. 5, 1. 5, 1. 2, 5. 2, 5. 2, 2. 2, 6. 2, 1. 6, 5. 6, 5. 6, 2. 6, 6. 6, 1. 1, 5. 2, 1, 5. 1, 2. 1, 2. 1, 6. 1, 6. And 1, 1. Right, so you can see this all automatically add up in here. So second one, look at that. This typically a little bit faster than the first one because you have set up for these ones. If you have third element, you can just copy these ones. You can have element number 3, land, and all these details, and you can make it element 3, K1, K2, K4, K4. Look at this. I can't check all the formula or anything here. You can see that.
Yeah.
So yeah, you can still put these details if you like because it's part of this one. No one's stopping. Sorry, something went wrong. Yeah, so what I'm saying that if you put this one in the Excels, like someone put these ones like this in the Excel, and then you put this one in the Microsoft Word, let's say like this,